Good morning, students. Welcome to Complex Analysis Live Lectures. In this lecture, we'll discuss analytic functions and their properties. Okay. So we'll start with definition of what is meant by analytic function. What is when we say that a function is said to be analytic. Okay. So a function f of complex variable z is said to be analytic at a point z naught if there exists some neighborhood of z naught in which f is differentiable everywhere throughout that neighborhood. That means if there exists a neighborhood of z naught in which f is f is differentiable throughout. That means what? Hmm? If you call it this as a n, say suppose if you call it there exists an n, that is f is differentiable for all z belongs to n. Is this clear? What is the definition of an analytic function? A function is said to be analytic at a point z naught. Hmm? So at least we should able to find some neighborhood of z naught. In that neighborhood, f is differentiable at every point. Is definition clear? Hmm? Hmm. Then we say that f, if you have this one, you can observe that with this, you can immediately have a remark that if f is analytic, at say z naught, then so what is the meaning of saying that? Before concluding writing the statement, what is up to here? What we know? There exists a neighborhood of z naught. So you have z naught. There exists a neighborhood of z naught in which f is differentiable everywhere in this one. Yes or no? Whatever point you take, f is differentiable. Now take this point. Suppose take this point. Okay. If I take this point, what can you say about this point? Whether f is analytic at this point? Hmm? This is my another point z, which is a point in this neighborhood. So can f is analytic at this point z is the question. Hmm? Why? What is yeah? What is the neighborhood? Hmm? What is the neighborhood? What is the neighborhood? You can take, so you take this distance, okay, right? Z minus Z naught, okay. Then you can find a neighborhood around that point, yes or no? Hmm? You can find a smaller neighborhood around this where inside this f is already differentiable, yes or no? Hmm? So given any point z, you can always find a smaller neighborhood which is completely contained inside this neighborhood, yes or no? And we know f is differentiable everywhere in that neighborhood. So therefore then f is analytic everywhere, analytic at all points in some neighborhood of z naught. Is that clear? By this definition we can understand this one. Any problem? Hmm? Now we say that again, if function f is said to be analytic on an open set if if it is differentiable everywhere in that open set. If f is differentiable everywhere in that open set. So whenever we want to say that f is analytic on an open set, then if it is differentiable at every point in that open set, then we say that it is analytic. Okay, is that clear? Hmm? And if we say that f is analytic on some set which is not an open set, then it is understood that there is some open set containing that set in which f is analytic. Okay, so whenever we say that f is analytic, it is always understood that there is some open set, okay, where f is analytic on that set. Yep. Fine. Now, so you can take a open set containing that closed set. Okay, so let me write that as a remark. So a function f is analytic on a set S which is not open means there exists an open set, okay, call it U, containing S such that f is analytic on U. Okay, so whenever we say that something f is analytic on a set, either that set should be open or there exists an open set containing that set where f is analytic. Is that clear? Hmm? So we are saying that suppose f is closed on a closed set at a closed interval, then f is analytic on an open set containing that given closed set. Okay. Hmm. That depends on your function. See, if you want to say that f is analytic on a set S is closed. Okay. For example, take a comma b. Then we should able to find a bigger set, okay, which is open and f is analytic everywhere. Then obviously f is analytic on this set also or not. Okay. So analytic we usually define for on analytic on a open set. So if at all you are saying that f is analytic on a set which is not open, it is understood that there is an open set containing that given set where f is analytic. Okay, fine. Now if f is differentiable, that means this is we have seen that this f is analytic, that means f is differentiable everywhere on this open set. Okay, now take your C complex plane or finite plane we can call it. If it is differentiable everywhere, every point in that complex plane, then we say that it is an entire function. Okay, so we will define what is meant by entire function. So a function f is said to be entire if it is differentiable at each point in the complex plane. That means you take any point in that complex plane, f should be differentiable at that point. Then we know that it is, we say that it is entire function. Okay. What is meant by analytic function? Analytic function means we define analytic function on a point and on an open set. So on that set, it should be differentiable. Okay. So if you take your open set U as your entire complex plane, then that means an analytic function on entire complex plane is called entire function. Is that clear? Hmm? It is differentiable everywhere in the complex plane means it is a analytic function on complex plane, right? Yes or no? Okay. Now, because this analytic is about differentiability on a given open set or on a given neighborhood, what we know, whatever properties hold for differentiable formulas like addition, then product, quotient, chain rule, okay, all these things you can apply for analytic functions also. That means you can write here as a simple remark, because analytic means analytic function, say you take on a domain means it is open and connected, right? So if you take f and g are two analytic functions on a given domain, or you take even it is differentiable at a point z naught. Okay, so if f and g are analytic on say some domain d, then what we can say, f plus g or f minus g, okay, this is analytic or not? Hmm? Is analytic on d. Similarly, f times g is analytic, right, on this domain, and also f upon g, okay, whenever g is non-zero, okay, right? This is also analytic. So sum, product and quotient of analytic functions are analytic. This simply follows from the differentiation formulas. Yes or no? You want to show that f plus g is analytic or not? Hmm? That means derivative of f plus g should exist everywhere in that domain. But we know f is analytic, so f dash exists everywhere, g dash exists everywhere, so f dash plus g dash exists everywhere. Right? Any problem? Hmm? Huh. Also, composition of analytic functions is also analytic. Okay. So wherever we are using this analytic, you can use these properties. Right? Now, let's see some examples so that we can understand, because we have not started with any example of analytic function. We'll talk about analytic at a point. So suppose take f of z, which is equal to 1 by z. Okay. Then what can you say about this function? Hmm? Where it is analytic? Hmm? Except, yeah, but so this is you are in complex plane. Okay. So clearly this function is not even defined at z is equal to 0, right? Okay. So you take, say suppose z is not equal to 0. When z is not equal to 0, then you can find the differentiation of this one. Hmm? Differentiation of this you can find or not? You can easily show that This differentiation exists everywhere except z is not equal to 0. Okay. So therefore, is analytic, this function is analytic at all non-zero points. Okay. Yes or no? Hmm? Obviously, what is f dash of z? Minus 1 by z square. Yes or no? Huh? Since f dash of z is equal to minus 1 by z square. You can verify this if you want. Okay. So this is an analytic function. It is analytic at all points except at 0. Suppose take this another one, f of z equal to say suppose mod z square. This one we have checked already this example. What can you say about this? Hmm? F of z is equal to mod z square. This is an example which we seen already. What do we know about this function? Hmm? This function we have shown that it is differentiable only at 0. Yes or no? Hmm? This is the function where it is differentiable only at one point, namely z is equal to 0. Remaining all places it is not differentiable. So what can you say about this function? Whether is it analytic at any point? Is it analytic at 0? Hmm? Is it analytic at 0? Why? See, there is a difference between analytic function and differentiable. Analytic at a point is more stronger than differentiable at that point. Huh? What is meant by analytic at a point? We should able to find some neighborhood around that point, okay, such that f is differentiable everywhere in that neighborhood, whereas differentiable at that point means that is very small one. So analytic at a point is more stronger than differentiable at that point. Is that clear? Huh. Yes. So now this function f of z is equal to mod z square, even though it is differentiable at 0, but it is not analytic at 0. Is that clear? Why? Because you take 0, okay, and you take any neighborhood around 0. It is not at all differentiable at any point you take. Yes or no? Hmm? So all these points f is not differentiable. However small neighborhood you take, however big you take, except at z is equal to 0, it is not differentiable. So since f of z is differentiable only at z is equal to 0, we can claim that f of z is not analytic at any point. F is not analytic, okay, at any point. Is that clear? Hmm? Because at other points there is no question, it is not even differentiable. What about at least 0? Even though it is differentiable at 0, but you take any neighborhood, there will be many points in that neighborhood where it is not differentiable. In fact, any point you take other than 0 in that neighborhood, it is not differentiable. Is this clear? Hmm? Yes or no? Okay. No, but this f of z is equal to 1 by z. If you take this 0, z is equal to 0. F is not analytic at z is equal to 0 because it is not differentiable. It is not even defined, right? Okay. But even though it is not analytic at that particular point, you take any neighborhood around 0. Other than that point, you can find remaining places it is differentiable. Yes or no? Hmm? Such points we will call it as singular points. We'll just define, and other properties we'll see later. That means what is meant by a singular point? A function f, uh, or you call it a point z naught, a point z naught is said to be singular point of given function f if if f, see, suppose f is not analytic at z naught, if f is not uh, analytic at z naught, you can call it f is not analytic at z naught, but that means it fails to be analytic at z naught, but uh, you take any neighborhood of z naught, there will be at least one point f is analytic, but f is analytic at some point, at some point uh, in every neighborhood, in every neighborhood of z naught. So let's understand again what is meant by a singular point. It, first of all, f should be failed to be analytic at z naught. Okay, that means there is no neighborhood where it is analytic at every point. Okay, but f is analytic at some point in every neighborhood of z naught. What is the meaning of this? Hmm? You take any neighborhood of z naught. Okay, f not necessarily be differentiable. Okay, at every point, but what is there is that there exists at least one point z, and here that means in this, see, you take a neighborhood z naught, then there is some point in which, at which f is analytic, means what, there exists some neighborhood of that z such that f is differentiable everywhere. Are you following? Yes or no? This f is differentiable. Clear? Hmm? So let me repeat again. A point is said to be singular point if, first of all, f is not analytic at z naught. That means whatever neighborhood of z naught you take, at least there will be one point where f is not differentiable. Is that clear? What is meant by saying f is not analytic at z naught? First, at least understand what is this one. When we say that f is not analytic at z naught, hmm, f is, go slow. What is meant by f is analytic at z naught? If you see here, what is meant by saying f is analytic at z naught? If there exists one, at least one neighborhood where f is differentiable everywhere in that neighborhood, right? Now, what is meant by saying that f is not analytic at z naught? Hmm? Say it clear. Hmm? When we say that this is false, huh? How? That means this should fail, right? Yes or no? So what is meant by saying that this condition is fail? Given any neighborhood, given any neighborhood of z naught, what we know, what we can say? At least there will be one point where f is not differentiable. Yes or no? F is analytic means at least you can find some neighborhood. Inside that neighborhood, every point it is differentiable. Now, what is meant by saying f is not analytic? Give me any neighborhood I can give one point in that neighborhood where f is not differentiable. Is that clear? Okay. Fine. Now come to the singular point. So singular point means f fails to be analytic at z naught, but f is analytic at least in one point in every neighborhood of z naught. So take any neighborhood of z naught, we can able to give one point at which f is analytic. That means we can able to find a small neighborhood around that z where f is differentiable. Is that clear? Hmm? It may be possible that in this neighborhood there are some points where f is not differentiable, but inside this f is differentiable. Clear? And this condition is true for all neighborhoods of z naught. Fine. Then we say that it is a singular point. Yes or no? Hmm? If you take f of z is equal to 1 by z, then whether 0 is a singular point or not, because we know already it is not analytic at 0, right? F is not analytic at 0 because it fails to be even defined at 0, right? It is not differentiable. Yes or no? Now question is whether 0 is a singular point or not. Then z is equal to 0 is a singular point. Why it is a singular point? That means what we want to prove? Take any neighborhood of 0. Take any neighborhood of 0, at least at one point it should be analytic. But what we know so much, so other stronger condition we know. We know that it is analytic everywhere except at 0, right? Yes or no? That means this is differentiable every point except at 0. So therefore 0 is a singular point. Are you following? Hmm? Yes. So if you take any neighborhood, this is 0. If you take any neighborhood other than 0, actually it is everywhere differentiable, right? So you take any point, it satisfies this condition. Because we require to it should be required analytic at only at some point. But what we have for this example is except 0 remaining all places it is already analytic. Yes or no? Okay. Just to understand, take this another example. Let me give that example. F of z, which is equal to z cube plus 4 upon z square minus 3 into z square plus 1. Okay. Then what can you say about this? What are the singular points here? That means where f fails to be analytic. See, this is what? This is just nothing but rational function or not? It is just like p of z by q of z, right? Yes or no? So if numerator is differentiable and denominator is differentiable wherever point, then obviously it is analytic. Yes or no? Here we have mentioned this, right? Whenever f and g are analytic and g is non-zero, then f by g is analytic. So it is all about numerator and denominator where they are not analytic. Okay. So if you consider this z square minus 3, this function is not even defined at z square equal to 3. Yes or no? Where this function has a problem, where this function is not defined at z square is equal to 3 and z square is equal to minus 1. Yes or no? So only at those points this function is not defined. Remaining all places it is defined. You can find the differentiation, everything, right? So f of z is analytic except at what are those points? Z square is equal to 3 means z is equal to plus or minus root 3 and z square is equal to minus 1 means z is equal to plus or minus I. Okay, right? Any problem? So now whether this plus or minus root 3 and plus or minus I, whether they are singular points or not, z is equal to plus or minus root 3 and z is equal to plus or minus I are singular points. Why they are singular points? Hmm? Everywhere. Huh? So suppose you take except at these points, suppose I take I here, okay, then you can take any neighborhood of this, whatever neighborhood you take around I, okay, you will have at least one point where f is analytic. Is this clear? Yes or no? See, suppose one point one should understand. Suppose I will take a bigger neighborhood of I, where this root 3 and minus root 3 are there. Now, what can you say about this neighborhood? Huh? Whether for this neighborhood also it is still true or not? Because except these 2 points, remaining everywhere it is differentiable. And what we require only condition is that at least one point it should be analytic in that neighborhood. Is that clear? Hmm? So we don't require that at every point in that neighborhood it should be analytic. It should be analytic at some point in every neighborhood of Z0. Clear? Hmm? Yes. Fine. Now let's see some properties of analytic functions, or you can also say when under what conditions a function is constant and so on. The first one, which we know already familiar in real analysis, that means real part, that if f dash of z is equal to 0 in a domain, say D, throughout that domain, okay, if you want throughout means at every point in that, then f is constant, which similar case is there. If f dash of x is equal to 0 for all x, then f has to be constant, right? That we know already in real case. Yes or no? So we'll prove that in this. It is true even for complex field also. That means complex plane. So f dash of z is equal to, that means it is f is differentiable and whose value is 0 in that throughout domain D, right? That means it is differentiable means CR equation satisfies, right? Yes or no? Say let f of z is equal to ux comma y plus I times vx comma y, right? Now since f dash exists in every point in this domain D, then CR equations are satisfied on D. Okay, that is ux is equal to vy, vx is equal to uy. Clear? Yes or no? What is given that yeah, very good. Vx is equal to minus uy. Good. Also, what is value of f dash of z in that case? How we have defined ux plus I times Vx. Is this clear? Hmm? So this implies ux plus I times Vx, which is equal to f dash of z, equal to 0 on entire D, right? Because f dash of z is equal to 0 is given to us. So a complex number is 0 means its real part and imaginary part should be 0, right? So therefore ux Vx is 0 on D, and using this CR equations Vy Uy also you will get 0, right? Yes or no? By ux, if ux is 0, then this ux is 0, that means Vy is 0, and Vx is 0 means Uy is 0. Yes or no? Then Vx is also 0 and Vy is also 0 on D. Okay. So what we got now is that partial derivatives of u and v with respect to x and y all are 0 on this entire domain D. That is what we got so far. Yes or no? Hmm? Now we will show that this f of z is constant by showing that u is constant and v is constant on this domain D. So we'll show that this u x comma y, okay, is constant on domain D. And similarly v is constant, so therefore f of z is some constant complex number. Is that clear? That is the idea. How we will show that u is constant? Using this ux is 0, vx is 0, okay, and this entire D. For that, let x naught comma y naught is a fixed complex number, or it is a point, okay, be fixed number, and you say L be a vertical line passing through this x naught comma y naught, passing through x naught comma y naught. That means what? How it look like? Hmm? This is L. You have a point, this x naught comma y naught, vertical line, right? Yes or no? So that is L is which is fixed, hmm? A vertical line and passing through x naught means x naught is fixed and y is any variable. Yes or no? Huh? Y belongs to R. Is this clear? So we have considered a line, and we'll define a function on this L. So define, say phi of y, a new function defined on L as u of x naught comma y. That means phi of y is the value of u when evaluated at x naught comma y. Is that clear? For example, phi of 0 is u evaluated at x naught comma 0. Phi of any real number, say root 2, then it is u of x naught comma root 2. Fine. Hmm? For all y belongs to R, real number. Okay. Then what can you say about phi dash of y? Phi dash of y is, that means this x naught is fixed and you are differentiating with respect to y or not. Therefore, it is same as uy. Hmm? Yes or no? But it is given that uy is 0. Okay. Ux where? Ux here you have to write uy, right? This is uy. This is uy. Ux, uy and vx. So this already it is there. So this is vy, right? Sir, no. So uy is 0 on D, right? So therefore phi dash of y is equal to 0 on D. Yes or no? Hmm? So now this is a real function which is 0 on D, that means this implies phi of y is constant, right? Constant on D. Phi of y is constant on D means that is same as saying that because our phi of y is u of x naught comma y, which is equal to constant. Whatever y it may be, it is constant. Yes or no? In particular, that value is equal to u evaluated at x naught comma y naught also, because this point is already there on that line. Yes or no? Okay. So therefore, we are getting u of x naught comma y is same as u of x naught comma y naught. Right? This is true for all y in that D. Clear? Okay. Okay. Now, similarly, by fixing, that means by taking a horizontal line, now we can take a horizontal line, okay, passing through that point x naught comma y naught, you can call it L prime. Yes or no? Then defining new function psi of y as u of x comma y naught, then ux is 0. Clear? So what you get? Similarly, so therefore, whatever we are having, this phi of x is constant on D or phi is constant on this vertical line is same as, you can prove that this is constant on horizontal line also. Clear? So what we will get? What we will get? So this u of say x comma y naught, okay, which is equal to u of x naught comma x naught comma y naught for all x belongs to D. Is this clear? Use horizontal line this time. Okay. Therefore, if you combine these two, what we will get? U of x comma, say you can call it here u of x comma y. U of x x naught comma y naught you take. This is same as u of x comma y naught. Okay. But now this is same as u of x comma y. Right? Any problem? So if you observe this, what you are getting that u of x where? Okay, let me write again. Let me write again. So because we want to show that u of x comma y is fixed and that value is, say you can u of x naught comma y naught. So you take u of x comma y, right? Now given x comma y and x naught comma y naught. So you have 2 points, x comma y and x naught comma y naught, right? X comma y is any arbitrary point and x naught comma y naught is given fixed point. Okay. Now this u of x comma y, this value is equal to what? What we can write? Yes. So you start with u of x naught comma y naught. Then from here it is same as u of x naught comma y, right? Okay. Now here this x naught and given y, this x naught and given y, from here what you will get? This u of x naught. So this is same as u of x comma y. That means you do here what we are changing in this last two, this first coordinate we are changing. Is that clear? Here only this is changed, right? In this one second one is changed and here the first one is changed. Okay, so this is true for given any x comma y, right? Any problem? So if we take this x comma y and here it is any x naught comma, here y is fixed, so x naught comma y, then and after that you take another line, okay, which is x naught comma y and the x naught comma y naught. Okay, then whatever we have discussed, u of x comma y, because u is constant on this horizontal line, is same as u of x naught comma y, and again it is constant in the vertical line, so therefore this is same as u of x naught comma y naught. So therefore u of x comma y is u of x naught comma y naught for all x comma y. This implies u is constant. Okay, so same way, similar way, we can prove that similarly v is also constant, of course constant on d, throughout d. Okay, this implies f of z, which is equal to u plus iv, is constant on or throughout d. Okay, so therefore if f dash of z is equal to 0, then and a domain d, then f of z is constant. As an application, we can see another result, interesting one, which says that if f of z and f z bar, conjugate of f of z, if both are analytic on d, then f of z is constant. Okay, so only function for which f and f bar both are analytic is the constant function. Okay, so proof is not difficult one. The idea is we'll use the earlier one, that means if we can, it is enough if we show that f dash of z is equal to 0 and d. For that, so let f of z, we denote f of z by ux comma y plus I times vx comma y, and capital this um, is implies f bar of z by, obviously it is ux comma y minus I times vx comma y. Just denote this by ux comma y plus I times vx comma y. Okay, uh, where this u is this small u and capital V is this small v times x comma y. Okay, this implies, that means you can write this ux comma y is same as small ux comma y, and capital Vx comma y is minus of small vx comma y. Now since f of z and fz bar, f and f bar both are analytic, they satisfy CR equations. Okay, um, as f and f bar both satisfies CR equations, we get, so one with respect to this f of z ux is one I'll write here, ux is equal to vy, and this is small v, and vx is equal to minus uy, and the other one, just I'll change the color, in terms of capital ux is equal to vy, and vx is equal to minus uy. Okay, but if we substitute this in terms of small, that means ux is same as small ux, okay, which is equal to, and what is capital Vy is minus small vy here. Okay, we are using these two, right, and Vx, which is same as minus Vx, is equal to Uy, which is, so the minus Uy we get, right. Now if we take this one, Ux is equal to Vy and Ux is equal to minus Vy, so therefore Ux is equal to Vy and Ux is equal to minus Vy, implies Ux is equal to 0, which is same as Vy. Yes, you will get 2 Ux is equal to 0, right? Similarly, this Vx is equal to minus Uy and Vx is equal to Uy. This implies Vx is equal to 0, which is same as Uy. So therefore, f dash of z, which is Ux plus I times Vx, is also 0, and d, right? This implies as f of z, f dash of z is equal to 0, so f of z is constant. Okay, this follows from previous theorem. Okay, fine. So next class we'll see some properties of other functions. Okay, we'll stop here. Thank you.